We're going to do a little bit of lecturing, and then we'll take a little break, and then we'll take our, I won't say final exam, we'll take our last exam here during the start of lab time. Okay, so we started talking about kinetics here, which is our last chapter that we're going to talk about. And remember that kinetics basically deals with how fast or how slow a reaction will take place. Um, and when we talk about sort of rates and of reactions, we talked about a couple different sort of ways we could figure out how things are changing. One was what is referred to sometimes as the rate expression. And the rate expression allows us to really understand how reactants, products, everybody's sort of changing, with time. And we could do that by sort of looking at an equation. And we could say that the rate is equal to minus 1 over the coefficient. So if you remember, that 1 over the coefficient takes care of all the really the stoichiometry part of it, kind of the multiple relationship, the change in the concentration of A over the change in time. Also remember that A is a reactant, so we would expect with time that the amount of reactants should start to decrease, while the amount of product should start to increase. We could also say that that is equal to minus 1 over B, again, minus because B is also a reactant, change in concentration of B over the change in time, and that would equal 1 over C, change in concentration of C over the change in time. Now, our C is a product, so as I just mentioned, we should expect it to be increasing with time, and that's why we don't have a negative in front of there. When we do calculate this, which is really the average rate for the reaction, this should usually always be a positive number, and that's also why the negatives are here for our reactants, because when we do the change in concentration of a reactant, the final concentration is always going to be smaller than the initial concentration. So when we do that sort of final minus initial for the, say, concentration of A, for example, it will always end up being a negative number. That negative number, along with the negative that we put in there because it's a reactant, will turn that negative and negative into a positive number for the rate. You could set them all equal to each other like I did here. You could kind of branch off and do each one individually equal to the average rate. And the nice thing about that is once you figure out the rate, it is all the rates. So these guys are all the same. So you can kind of put them equal to each other and stuff of that nature. We then started talking about the rate law, and the rate law is a little bit different. It does deal with really just our reactants, and rate laws typically look something like this. The rate is equal to K times the concentration of A to the X and say B to the Y. X and Y are what are referred to as orders. And if you add them together, take like X plus Y, that will equal the overall order of the reaction. And basically, as we talked about last time, these guys are always found, our rate laws and orders and all those things are really always found experimentally, which means for the most part, you typically in these type of problems, as we saw last time, are given like a data table. And in that data table, there's like the concentration of A, there's concentration of B, they have some initial rates happening in like molarity per seconds. And maybe there's 1 trial, 2 trials, 3 trials, 4, however many trials. And remember that when we take this table, we could sort of mathematically solve for X and Y by using the information in there and using sort of this math equation, which is kind of like the rate 2 divided by the rate 1 is equal to K times A to the X and B to the Y, B to the Y, no Y inside, divided by K A to the X and B to the Y here. And again, as we talked about last time, I think we did an example there at the end. When we talk about rate 1 and rate 2, we're not talking about go to the table and pick the first and second entry. What we're talking about is when you go to this table, you want to pick two entries where one of the concentrations remains the same and the other one varies. And that's going to allow you to basically figure out, what X is and what Y is. You'll eventually get to something like we saw, like, hey, 4 is equal to 2X. And you can figure out, hey, X is equal to 2 in that particular case. Again, you can take the natural log of both sides and divide it, is also mathematically how you could do that as well. Or you could just kind of look at it in a lot of cases and sort of see the number. Any questions on that stuff we sort of talked about last time? Now, just to sort of summarize some of that stuff, specifically about the rate law that we talked about, and by the way, the little k is the rate constant. And I think we also sort of talked about last time that, you could use sort of the orders and the rate law. The orders are sort of like, again, the proportion of those reactants that need to come together to make a specific rate. And we could use it to do things like, if we wanted to slow down the reaction, we could play with the concentrations. If we want to increase the rate of the reaction, we could play with the concentrations and stuff like that. So for example, I think maybe last time we looked at one where, if we like doubled, say, B's concentration, the rate of the reaction went up by like 4-fold or something like that. So, you could kind of use rate laws and those orders to do those things, sort of manipulate how fast or slow a reaction may take place. But when we talk about rate laws, again, they're always determined experimentally, which means you should always probably have some type of data table probably given to you in problems. The reaction order is always in terms of the reactants, not the products. So when we write rate laws, it's all about only the reactants are involved in here. So really only reactants, no products. And the order, as we've just been mentioning, is not really the coefficient in the balance equation. It does need to be found sort of experimentally. Sometimes they are the same, but that is not directly how we get it. For example, if you go and take 1B or 200B, you do a lot of equilibrium where that is where you sort of get those values from, is the coefficients, but we don't do it here in this type of calculation. So here the rate equation for this reaction of NO with ozone is the rate is equal to K times the concentration of NO and O2. If the rate is 6.6 times 10 to the minus 5 molar seconds, when the concentrations are there, what is the rate constant? So in this particular case, they actually gave us the rate law, which is the rate is equal to K times NO and O3. We have the rate given to us. We have the concentrations of these guys given to us. We can rearrange this equation and solve for K, which is the rate constant. By the way, with nothing written here, it means it's first order with NO, and it is first order with O3 in this particular case. That means this is a second order reaction overall. So rearrange this equation will give us K is equal to the rate divided by NO and O3. Putting it in gives us 6.60 times 10 to the minus 5 molar seconds divided by NO, which is 1 times 10 to the minus 6 molar, times our 3 times 10 to the minus 6 molar. And that will give us a rate constant here of looks like 2.20 times 10 to the 7. Now, what are the units here? Molarity on top and a molarity on the bottom are going to cancel. It does give us units of 1 over molar seconds. And 1 over molar seconds are the typical units for the rate constant that we actually do associate with a second order reaction. So that does make sense. And as we'll see here a little bit later on in this chapter, by just knowing the units associated with the rate constant, it will tell you what type of order reaction it is. Any questions on that calculation there? It's a fairly high rate constant, right? So probably moving fairly quickly here. All right, so why don't you give this one a go and see what you come up with. We want to figure out what is the completed rate law. with the orders, why don't you also figure out the overall order of the reaction? And why don't you also figure the value of the rate constant? So take a couple minutes and see what you come up with here. Okay, so let's take a look just to make sure everybody, again, is still on the right track. We could start with just the generic rate law here without sort of the orders in it. And again, it would be made up of just our reactants. So S2O8 2 minus to the X and I minus to the Y. Again, our goal here is really to find what X and Y is using the table information there. And remember that when we go to this table, what we're looking for is two entries where one of the concentrations remains the same and the other one varies. So if we look at entry 1 here and entry 2, we see that the concentration of our first guy there does remain the same. So we're going to pick those two to start with. So we're going to go with 1 and 2 here. Let me get my thing to right. There we go, 1 and 2. So as I also mentioned last time, sometimes it's helpful to kind of put the larger rate guy up on top. It does, you don't have to, but it sometimes gives you a little bit more kind of whole numbers, makes it a little bit easier. So what I'm going to do is put all the information from experiment 1 all the way across on top. That gives me 2.2 times 10 to the minus 4. It's going to equal K times 0.08 to the X, 0.034 to the Y. And again, that's all the information that comes from experiment 1 from the table. I'm then going to put experiment 2's information all the way across on the bottom. And that gives me this guy here and this one here. Now we're going to do a little bit of math here. So when we divide these guys out, pretty much get a 2. As we talked about last time, K on top and K on the bottom is the rate constant. Although we don't know what it is at this point, it is a constant number, which means they should cancel out. When we come over here to 0.08 to the X and 0.08 to the X, again, we do not know what X is at this point, but it is the same number on top and bottom. So we know that these guys will also cancel out. And if we just divide out the next guy, that looks like a 2 to the Y here when you do that. Now you could probably just visually look at this and see that Y would equal 1. Again, if you're not sure, you would take the natural log of 2 as one way to do it. Natural log of 2 will bring the Y to the bottom. You could divide by the natural log of 2, in this case, to both sides. Those guys will cancel. This will give us 1. So if you happen to get one where it's not really pretty numbers or decimals or something like that, that's one approach as to how you could kind of solve for it. Just basically take the natural log of both sides and then divide it out. Any questions so far on that part of the calculation? So now that we kind of kept this guy constant, what we want to do now is go back to the table and keep the other one constant. And in this case, it looks like experiment 2 and experiment 3 will do that for us. It'll keep those guys constant. And we're just going to basically do the same thing. In this case, I see number 3 looks like the higher rate. So I'm going to put numbers 3's information all the way across here. And now I'm going to put number 2's information all the way across on the bottom. And again, if we do our math, that is going to give us a 2. Same idea here, K and K will be the same. The Y and the Y will be the same. When we do the division here, we get 2 to the X, and in this case, X is going to equal 1 in this case. Again, a reminder, it won't always equal 1. It just happened to be in these examples here. Any questions on that so far? Now that we got the orders, we could actually write the completed rate law, which would technically be the rate is equal K to the S2O82 minus to the first, but we don't have to put the 1 because it's a 1. times I minus, also to the first. Again, we don't typically put the ones there when we write the rate law. Any questions on that one there? Now, the rest of what we're looking for here is what is the overall order? And the overall order is found by adding up the individual orders, X, Y, Z, however many you have. In this case, 1 plus 1 tells us it is second order. At this point, we now can use our completed rate law and rearrange it and solve for K and actually find what the value of K is. And if we rearrange it in this case, K would equal the rate divided by the S2O82 minus and the I minus concentration. Putting in our numbers, which we could absolutely take experiment 1's information to R3. You could take any one of these guys, and they all should give you pretty much the same K value. So I'm just going to take experiment 1, for example, which would give me 2.2 times 10 to the minus 4 molar seconds, divided by our 0.08 molar and our 0.34 molar. And that will yield us a rate constant of 2.2 to the minus 4 divided by 0.08 divided by 0.034. Looks like maybe 0.081. And what are the units here? Molarity on top and a molarity on the bottom will cancel, giving us our 1 over molar seconds. And again, perhaps you can see a theme. 1 over molar seconds, as we saw just a second ago, again, are the units typical of a second order sort of rate law overall. Any questions on where any of the numbers came from? Okay. Why don't we try one more here just to make sure? Let's find the same things, just do the rate law, the overall order, and the value of K. All right, so see what you come up with in this case. Okay, so we'll do the same approach here. We're going to just start out with the basic sort of generic rate law, which would be something like the rate is equal to K. Again, just our reactants involved here. So NH4 plus to the X, a little NO2 minus there to the Y. Here we actually have 4 entries, and as I mentioned last time, we could have 4 entries, 5, 6, 7, a whole bunch. Usually we'll at least have 3. And we're just going to kind of do the same thing. We're going to look for where we can keep one constant. So it looks like if we actually take 1 and 2 here, we could keep the NO2 minus constant. So we'll start with that. Using 1 and 2, we're going to put the larger value up on top in terms of the rate. So that's going to be 32.3. And a reminder that you do want to make sure you read the title there, or the column, because that's actually times 10 to the minus 7, which may not make a difference in this part of the calculation, but will make a difference in terms of the rate constant calculation that you might do. Now we're going to put everything from number, I think I threw the wrong ones in the wrong spot. I did. So that's a 6 and that's a 2. That's good. So now that I correctly did it, everything for number 2 up there on top. And now I'm going to put everything for number 1 on the bottom. Again, bad scientific notation here. We'll do that. And 0.02 to the X, 0.2 to the Y. So when we do a little division there of 32.3 to the minus 7 divided by 10.8 to the minus 7, going to basically give us 2.99 is going to equal K, and K should cancel. These guys here should cancel. These guys should get us to basically 3 to the X. This probably is close enough for you to round up to a 3. And you can then probably visually see it that x should equal 1 in this case. Again, will not always equal 1, just happen to be in these couple of examples here. And again, if you did the natural log of both sides, you would end up with an x value of 0.997, which is fairly close to 1. So you can do a little bit of rounding here. It's usually not a big issue in terms of your final number there. Now that we kept the NO2 minus, we want to go back now and keep our other one constant. And it looks like that perhaps number 3 here and number 4 will do that for our NH4 plus. So doing those two, which is 3 and 4, again, going with the larger value there up on top. So we're going to put all those guys across the top. Going to give us 21.6 times 10 to the minus 7. Our K, our 0.2 to the X, 0.0404 to the Y. Coming back across and putting our number 3 all the way across, 10.8 times 10 to the minus 7. Our K, 0.2. And our 0.0202 to the Y. This here, doing that division there, 21.6 divided by 10.8, going to give us a 2, is equal to, again, going to cancel, and 2 to the Y. Y here, again, equaling 1. So we now have our orders for this guy. And the rate would equal K NH4 plus and NO2 minus, again, both to the first order, which means that overall we should have 1 plus 1, which equals, again, second order here. Now we can isolate our rate constant and solve for it. So K would equal the rate divided by NH4 plus and NO2 minus. And just like before, you really can take, any entry you like off this table. I'll just, again, take the first one, but you really could do the second if you want to, third or fourth. It should all come out the same. Putting the information for the first one in, and this is really where it's important that you do the minus 7. Otherwise, you will definitely be off. Divided by our 0.02 molar and our 0.2 molar. At this point, 10.8 to the minus 7 divided by 0.02 divided by 0.2, going to give us 2.7 to the minus 4. And again, molarity and a molarity here will cancel, and that will again leave us our 1 over molar seconds that we've been seeing, that is, again, associated with a second order reaction. Any questions on how to use these tables to figure out the orders of reactions or the rate law or anything like that? And maybe there's a question, so just to make sure everybody does understand, let's just say, hypothetically speaking, we did this guy and we did get that the rate was, for example, K NH4 plus to the second and NO2 minus to the first. Let's just say hypothetically this is what it came up. First off, it would mean that the overall order here would be third order, second plus 1, which would be third. And also when we would go solve for K, for example, we do have to take that square into account. So K in this case would equal the rate divided by NH4 plus squared and NO2 minus. So you would have to take that into account if you happen to get, obviously, something other than 1. You would need to square it when you're doing something like solving for K and stuff like that. Obviously, it didn't happen in this case, but it definitely does happen along the way. Also, another thing that comes up that sometimes stumps people is, if you have, like, say 4 to the X is equal to 1, that is basically going to mean that X is equal to 0, right? So something to the 0 power will equal 1 if you have something like that. And that's something that does also come up a lot in kinetics and stuff like that. Any questions on how to do these type of problems here? Okay. So now that we've talked about sort of rate laws in general, we're going to talk about specific orders of reactions and sort of some differences between these different orders and what's sort of going on here. The first type of reaction deals with what are sometimes referred to as first order reactions. First order reactions, much like the name implies, means that we pretty much can have one reactant with an order to 1, which gives us first order. You could also have 2 reactants where 1 is maybe first order, 1 is 0 order. We'll also give you overall order of first order and stuff like that. If we write the rate law, it will look something like this. The rate is equal to K times concentration of A. Rearranging it and solving for the rate constant here gives us one really important piece of information about first order reactions, and that is the units that are associated with the rate constant. The units typically associated with the rate constant is 1 over reciprocal, or 1 over seconds, or reciprocal seconds. Although it does not necessarily have to be seconds, it could be 1 over minutes, 1 over hours, 1 over days, weeks, so forth. Most of the time we do deal with seconds. So if we do some type of chemical reaction, typically we're following it over a period of seconds and stuff like that, rather than sitting there for hours or days or weeks. But they technically can be any unit of time. So why is that important? It's important because sometimes in problems, they will not in flashing lights go, hey, you're dealing with a first order reaction. They will tell you the value of the rate constant. And from the units that you see from that rate constant, for example, 1 over seconds should tell you that you're dealing with a first order reaction. Why is that important? Well, when we want to figure out something like how the concentration is changing with time or something like that, we have this concentration and time dependent rate law, which is sometimes referred to as the integrated rate law. And this gives us a couple of things here. This A, this first, is kind of like your final concentration. This little A with the naught is like your initial concentration. K is our rate constant. And T here is actually time. So not temperature, but time here. And this allows you to, if you know the initial concentration, how long something is, you could figure out, how much will be left over. If you know sort of, the initial and the final, you can figure out how long it would take for that to occur. So there's a lot of information you could do with this. We also have another equation that goes with it for first order, and that is the half-life equation. And that's the natural log of 2 divided by the rate constant. What is the half-life? The half-life is the time it takes for half of whatever you started with to kind of go away. If you started with 10, after the first half-life, you'll be left with 5. After the second half-life, 2.5. After that, I need a calculator, but you keep dividing by 2, and that's pretty much what you're left with. Now, if we take this equation here, this integrated rate law, which basically comes from taking the natural log of this equation here, we get this equation that looks something like this. If we kind of rearrange it, where the natural log of A is equal to minus KT plus the natural log of A naught. And that equation is basically rearranged and written in the form of a straight line, which is y is equal to mx plus b. That means that the typical graph that we associate with first order is on the y, the natural log of A, and on the x, we have time. And if you do that, you will yield yourself a straight line like we see here. And the slope of that line will actually equal minus k, or minus the rate constant, as you can see here. So the slope will equal minus k. The slope of this line will be a negative number, along with the negative here. We'll turn our rate constant into a positive number in this particular case. So the rate constant should be a positive number. And again, because the actual line itself, if you got the slope value, will be negative, with that extra negative there, we'll turn our rate constant into a positive number. What do we see if we just graph the concentration versus time? We see what we expect to happen. Early on in the time, we have a lot of A. And as time kind of goes on, we're seeing a decrease with A overall as the time goes by. Again, A being the reactant, we would expect that to happen. So what information do you really need to know here from first order, which is really important? It is a couple of things. The value or the units of the rate constant for first order is basically 1 over seconds or 1 over time. The integrated rate law is important, and the half-life equation here is important, and the actual graph that most people associate with in terms of first order is that guy on the right, that straight line graph. Now, a lot of times, a couple of things that oftentimes come up, and that is you oftentimes will have to use kind of both of these equations together. And that's because there'll be a situation where, you have everything but the rate constant. So you may be given the half-life, you can find the rate constant, and then go into this equation to do it. The other really important part of this calculation is that last part here, the K and the T. T is time, which sometimes are in different units than the rate constant. So maybe this guy is 1 over seconds. You want to make sure that your time's in seconds so that they cancel. But sometimes your time might be in minutes, it might be in weeks, days, or something like that. So sometimes you have to do a conversion between the time and the rate constant to get the sort of time unit into the right sort of guy there. Any questions on that there? Here's again a plot that is very common, which is again our natural log of our concentration versus time, and that does give us a straight line. I have a lot of things circled under the natural log of 2. That is K. That's the rate constant, if that's what you're asking. Yeah, it's a really bad K. So it's the rate constant. It's a natural log 2 divided by the rate constant. Other questions on that? Okay, so if we take a look at one here, the reaction is first order with A and with a rate constant of 2.8 times 10 to the minus 2 seconds, reciprocal seconds. How long will it take A to decrease from 0.88 to 0.14? So why don't you take a couple minutes here and see what you come up with. Okay, so let's take a look here. A couple of things. They were nice enough to tell us that it is first order. If they didn't, we would know it's first order by looking at the units of the rate constant here, which is K, and we see it's 1 over seconds or reciprocal seconds, and that automatically tells us that we are dealing with first order. Why that's important is we would know that we would want to use the first order integrated rate law, which is this guy, and this guy is different than, say, second order or something like that, or zero order, which we'll talk about as well. So we have this guy here. So we got a couple of things here. We obviously have K given to us, which is 2.8 times 10 to the minus. I scribbled on it. I think that's a 2 reciprocal seconds. We have the 0.88, which is actually the initial concentration. And the final concentration is the 0.14. Remember, A is a reactant, so it should be decreasing with time. So we got everything we need except for T, which is time. So putting that stuff in gives us the natural log of our final concentration is equal to the natural log of our initial concentration minus the rate constant times T. How I would do this is I would take the natural log of 0.14 hit equals, then subtract the natural log of 0.88. So bringing this to the other side and subtracting it. Natural log of 0.88. That's going to give me something like minus 1.88 838,279 is equal to minus 2.8 times 10 to the minus 2 reciprocal seconds times t. I'm then going to divide this to the other side along with the negative. It's going to come on over to the other side there. These guys are going to obviously cancel. And if I do that, 2.8 to the minus 2, looks like I end up with about 66 seconds in this case. It is seconds because really the rate constant here, when we divide it over, it's 1 over seconds. When you divide it, the seconds flip to the top. And it'll take about 66 seconds for that to occur in this type of reaction. Any questions on that there? Okay. All right, so I think what we'll do, we'll lay it up there.